In the name of Almighty God, I'm Mahsa Sankashi, and today I want to talk about stress strain analysis in SolidWorks. Stress strain analysis or stress analysis is an engineering discipline that uses many methods to determine the stresses and strains in materials and structures subjected to forces. In continuum mechanics, stress is a physical quantity that expresses the internal forces that neighboring particles of a continuous material exert on each other, while a strain is the measure of the deformation of the material. In simple terms, we can define stress as the force of the resistance per unit area offered by a body against deformation, and stress is the ratio of force over area, which S is equal to R divided by R, where S is the stress, R is the internal resisting force, and R is the cross-sectional area. Strain is the ratio of change in length to the original length when a given body is subjected to some external force, which strain is equal to change in length divided by the original length. Stress analysis is a primary task for civil, mechanical, and aerospace engineers involved in the design of structures of all sizes such as the tunnel, bridges, and dams, aircraft and rocket bodies, mechanical parts, and even plastic cutlery and staplers. Stress analysis is also used in the maintenance of such structures and to investigate the causes of structural failures. Typically, the starting point for stress analysis are a geometrical description of the structure, the properties of the materials used for its parts, how the parts are joined, and the maximum or typical forces that are expected to be applied to the structure. The output data is typically a quantitative description of how the applied force is spread throughout the structure, resulting in stresses, strains, and the deflections of the entire structure and each component of that structure. The analysis may consider forces that vary with time, such as engine vibrations or the load of moving vehicles. In that case, the stresses and deformations will also be functions of time and space. In engineering, stress analysis is often a tool rather than a goal in itself, the ultimate goal being the design of structures and aircrafts that can withstand a specified load using the minimum amount of material or that satisfies some other optimality criteria. Stress analysis may be performed through classical mathematical techniques, analytic mathematical modeling, or computational simulation, experimental testing, or a combination of methods. The term stress analysis is used throughout these art simulation for the sake of uh, brevity, but it should be understood that the strains and deflections of structures are of equal importance, and in fact an analysis of a structure may begin with the calculation of deflections or strains and in the with calculation of the stress. And what about the chapter of scope? The general principles. Stress analysis is specifically concerned with solid objects. The study of stresses in liquids and gases is the subject of fluid mechanics. Stress analysis adopts the macroscopic view of materials characteristics of continuum mechanics, namely that all properties of materials are homogeneous at small enough scales. Thus, even the smallest particle considered in a stress analysis still contains an enormous number of atoms, and its properties are averages of the properties of those atoms. In stress analysis, one normally disregards the physical causes of forces or the precise nature of the materials. Instead, one assumes that the stresses are related to the strain of the material by non-constitutive equations. By Newton's law of motion, any external forces that act on a system must be balanced by internal reaction forces or cause the particles in the affected part to accelerate. In a solid object, all particles must move substantially in concrete to maintain the object's overall shape. It follows that any force applied to one part of a solid object must give rise to internal reaction forces that propagate from the particle to particle throughout an extended part of the system. With very rare exceptions such as ferromagnetic material or planet-scale bodies, internal forces are due to very short-range intermolecular interaction and are therefore manifested as surface contact forces between agents and particles, that is, as stress. Fundamental problem. The fundamental problem in stress analysis is to determine the distribution of internal stresses throughout the system given the external forces that are acting on it. In principle, that means determining implicitly or explicitly the Cauchy stress tensor at every point. The external forces may be body forces such as gravity or magnetic attraction that act throughout the volume of a material, or concentrated loads such as friction between an axle and a bearing or the weight of a train wheel on a rail, that are imagined to act over a two-dimensional area or along a line or at single points. The same net external force will have a different effect on the local stress depending on whether it is concentrated or spread out. Types of structures. In civil engineering applications, one typically considers structures to be in a static equilibrium, that is, are either unchanging with time or are changing slowly enough for viscous stresses to be unimportant, quasi-static. In mechanical and aerospace engineering, however, stress analysis must often be performed on parts that are far from equilibrium, such as vibrating plates or rapidly spinning wheels and axles. In those cases, the equations of motion must include terms that account for the acceleration of the particle in structural design applications. One usually tries to ensure the stresses are everywhere well below the yield strength of the material. In the case of dynamic loads, the material fatigue must also be taken into account. However, these concerns lie outside the scope of stress analysis proper being covered in material science under the name strength of materials. Fatigue analysis, stress corrosion, creep modeling, and other. The chapter of experimental methods. Stress analysis can be performed experimentally by applying forces to a test element or structure and determining the resulting stress using sensors. In this case, the process would more properly be known as testing. Destructive or non-destructive experimental methods may be used in cases where mathematical approaches are cumbersome or inaccurate. Special equipment appropriate to the experimental method is used to apply the static or dynamic loading. There are a number of experimental methods that may be used. The first one is tensile testing. Is a fundamental material science test in which a sample is subjected to an uniaxial tension until failure. The results from the test are commonly used to select a material for an application for quality control or to predict how a material will react under other types of forces. Properties that are directly measured via a tensile that tests are the ultimate tensile strength, maximum elongation, and reduction in cross-section area. From these measurements, properties such as Young modulus, Poisson ratio, yield strength, and strength hardening characteristics of the sample can be determined. The next one is strain gauges. can be used to experimentally determine the deformation of a physical part. A commonly used type of strain gauge is a thin flat resistor that is affixed to the surface of a part and which measures the strain in given direction. From the measurement of strain on a surface in directions, the stress state that developed in the part can be calculated. Neutron diffraction is a technique that can be used to determine the subsurface strain in a part. The next one is the photoelastic method relies on the fact that some materials exhibit a brief fringiness on the application of stress, and the magnitude of the refractive indices at each point in the material is directly related to the states of stress at that point. The stresses in the structure can be determined by making a model of the structure from such a photoelastic material. The next one is dynamic material analysis is a technique used to study and characterize viscoelastic material, particularly polymers. The viscoelastic property of a polymer is studied by dynamic mechanical analysis where a sinusoidal force stress is applied to a material and the resulting displacement strain is measured. For perfectly elastic solid, the resulting strains and the stresses will be perfectly in phase. For a purely viscous fluid, there will be a 90-degree phase lag of strain with respect to stress. Viscoelastic polymers have the characteristics in between where some phase lag will occur during DMA test or dynamic mechanical analysis test. The chapter of mathematical methods. While experimental techniques are widely used, most stress analysis is done by mathematical methods, especially during design. The differential formulation. The basic stress analysis problem can be formulated by Euler's equations of motion for continuous bodies, which are consequences of Newton's law for conservation of linear momentum and angular momentum, and the Euler-Cauchy stress principle together with the appropriate constitutive equations. These laws yield a system of partial differential equations that relate the stress tensor field to the strain tensor field as unknown functions to be determined. Solving for either then allows one to solve for the other through another set of equations called constitutive equations. Both the stress and strain tensor fields will normally be continuous within each part of the system, and that part can be regarded as a continuous medium with smoothly varying constitutive equations. The external body forces will appear as the independent right-hand side term in the differential equations, while the concentrated forces appear as boundary conditions. An external applied surface force, such as ambient pressure or friction, can be incorporated as an imposed value of the stress tensor across that surface. External forces that are specified as line loads such as traction or point loads such as the weight of a person standing on a roof introduce singularities in the stress field and may be introduced by assuming that they are spread over a small volume or surface area. The basic stress analysis problem is therefore a boundary value problem. The chapter of elastic and linear cases. A system is said to be elastic if any deformations caused by applied forces will spontaneously and completely disappear once the applied forces are removed. The calculation of the stresses, stress analysis that develop within such systems is based on the theory of elasticity and infinitesimal strain theory. When the applied loads cause permanent deformation, one must use more complicated constitutive equations that can account for the physical process involved plastic flow, fracture, phase energy change, and etc. Engineered structures are usually designed so that the maximum expected stresses are well within the realm of linear elastic. The generalization of Hooke's law for continuous media behavior for the material from which the structure will be built, that is, the deformations caused by internal stresses are linearly related to the applied loads. In this case, the differential equations and the define and the stress tensor are also linear. Linear equations are much better understood than nonlinear ones for wanting their solution, the calculation of stress at any desired point within the structure will also be linear function of the applied forces. For a small enough applied loads, even nonlinear systems can usually be assumed to be linear. Built-in stress or preloaded. A preloaded structure is one that has internal forces, stresses, and strains imposed within each by various means prior to application of externally applied forces. For example, a structure may have cables that are tightened, causing forces to develop in the structure before any other loads are applied. Tempered glass is a commonly found example of a preloaded structure that has tensile forces and stresses that act on the plane of the glass and in the central plane of glass that causes compression forces to act on the external surfaces of that glass. The mathematical problem represented is a typical ill-posed because it has an infinitude of solutions. In fact, in any three-dimensional solid body, one may have infinitely many and infinitely complicated non-zero stress tensor fields that are in a stable equilibrium even in the absence of external forces. These stress fields are often termed hyperstatic stress fields, and they coexist with the stress fields that balance the external forces. In the linear elasticity, their presence is required to satisfy the strain displacement compatibility requirements, and in limit analysis, their presence is required to maximize the load carrying capacity of the structure or component. Such built-in stress may occur due to many physical causes, either during manufacturing process like extrusion, casting, or cold working, or after the fact, for example because of uneven heating or changes in moisture content or chemical composition. However, if the system can be assumed to behave in a linear fashion with respect to the loading and response of the system, then the effect of periload can be accounted for by adding the results of preloaded structure and the same non-preloaded structure. If linearity cannot be assumed, however, any built-in stress may affect the distribution of internal forces induced by applied loads, for example by changing the effective stiffness of the material or even cause an unexpected material failure. For these reasons, a number of techniques have been developed to avoid or reduce built-in stress, such as annealing of cold-worked glass and metal parts, expansion joints in a building, and roller joints for bridge. The chapter of simplification. Stress analysis is simplified when the physical dimensions and the distribution of loads allow the structure to be treated as one or two-dimensional. In the analysis of a bridge, each three-dimensional structure may be idealized as a single planar structure. If all forces are acting in the plane of the trusses of the bridge, further each member of the truss structure might then be treated as unidimensional members with the forces acting along the axis of each member, in which case the differential equations reduce to a finite set of equations with finitely many unknowns. If the stress distribution can be assumed to be uniform or predictable or unimportant in one direction, then one may use the assumption of plane stress and plane strain behavior, and the equations that describe the stress field are then a function of two coordinates only instead of three. Even under the assumption of linear elastic behavior of the material, the relation between the stress and strain tensors is generally expressed by a force-order stiffness tensor with 21 independent coefficients, symmetric 60 multiplied by 60 stiffness matrix. This complexity may be required for general anisotropic materials, but for many common materials it can be simplified. For orthotropic materials such as wood, whose stiffness is symmetric with respect to each of the three orthogonal planes, non-coefficients suffice to express the stress-strain relationship. For isotropic materials, these coefficients are reduced to only two. One may be able to determine a period that in some parts of the system the stress will be of a certain type, such as uniaxial tension or compression, simple shear, isotropic compression or tension, torsion, bending, and etc. In those parts, the stress field may then be represented by fewer than six numbers and possibly just one. The chapter of solving the equations. In any case, for two or three-dimensional domains, one must solve a system of partial differential equations with specified boundary conditions. Analytical closed-form solutions to the differential equations can be obtained when the geometry, constitutive relations, and boundary conditions are simple enough. For more complicated problems, one must generally resort to numerical approximations such as the finite element method, the finite difference method, and the boundary element method. The chapter of factor of safety. The ultimate purpose of any analysis is to allow the comparison of the developed stresses, strains, and deflections with those that are allowed by design criteria. All structures and components therefore must obviously be designed to have a capacity greater than what is expected to develop during the structure's use to obviate failure. The stress that is calculated to develop in a member is compared to the strength of the material from which the member is made by calculating the ratio of the strength of the material to be a calculated stress. The ratio must obviously be greater than 1 zero if the member is two not to fail. However, the ratio of the allowable stress to the developed stress must be greater than 1 as a factor of safety. Design factor will be specified in the design requirements of the for the structure. All structures are designed to exceed the load those structures are expected to experience during their use. The design factor, a number greater than 1, represents the degree of uncertainty in the value of the loads, material strength, and the consequences of failure. The stress or load or deflection the structure is expected to experience are known as the working, the design or limit stress. The limit stress, for example, is chosen to be some fraction of the yield strength of the material from which the structure is made. The ratio of the ultimate strength of the material to the allowable stress is defined as a factor of safety against ultimate failure. Laboratory tests are usually performed on material samples in order to determine the yield and ultimate strength of those materials. A statistical analysis of the strength of many samples of a material is performed to calculate the particular material strength of that material. The analysis allows for a rational method of defining the material strength and results in a value less than, for example, 99.99% of the value from the samples tested. By that method, in a sense, a separate factor of safety has been applied over and above the design factor of safety applied to a particular design that uses a said material. The purpose of maintaining a factor of safety on yield strength is to prevent detrimental deformations that would impair the use of the structure. An aircraft with a permanently bent wing might not be able to move its control surfaces and hence is inoperable. while yielding of material or the structure could render the structure unusable, it would not necessarily lead to the collapse of the structure. The factor of safety on ultimate tensile strength is to prevent sudden fracture and collapse, which would result in greater economic loss and possible loss of life. An aircraft wing might be designed with a factor of safety of 1.25 on the yield strength of the wing and a factor of safety of 1.5 on its ultimate strength. The test fixtures that apply those loads to the wing during the test might be designed with a factor of safety of 3 on the ultimate strength, while the structure that shelters the test fixture might have an ultimate factor of safety of 10. These values reflect the degree of confidence the responsible authorities have in their understanding of the load environment, their certainty of the material strength, and the accuracy of the analytical techniques used in analysis, the value of structures, the value of the lives of those flying, those near the test fixtures, and those within the building. The factor of safety is used to calculate the maximum allowable stresses, which is if the formula is maximum allowable stress is equal to ultimate, un, ultimate tensile stress divided by factor of safety. The chapter of load transfer. The evaluation of load and stresses between structures is directly to finding the load transfer path. Loads will be transferred by physical contact between the various component parts and between structures. The load transfer may be identified visually or by simple logic for simple structures. For more complex structures, more complex methods such as theoretical solid mechanics or numerical methods may be required. Numerical methods include direct stiffness method, which is also referred to as the finite element method. The object is to determine the critical stresses in each part and compare them to the strength of the material. For parts that have broken in service, a forensic engineering or failure analysis is performed to identify weakness, where broken parts are analyzed for the cause or causes of failure. The method seeks to identify the weakest component in the load path. If that is the part which actually failed, then it may corroborate independent evidence of the failure. If not, then another explanation has to be sought, such as a defective part with a lower tensile strength than it should, for example. Uniaxial stress chapter. A linear element of structure is one that is essentially one-dimensional and is often subject to axial loading only. When a structural element is subjected to tension or compression, its length will tend to elongate or shorten, and its cross-sectional area changes by an amount that depends on the Poisson ratio of the material. In engineering applications, such members experience small deformations, and the reduction in cross-sectional area is very small and can be neglected. For example, the cross-sectional area is assumed constant during deformation. For this case, the stress is called engineering stress or nominal stress and is calculated using the original cross-section, which is sigma E is equal to P divided by R0, where P is the applied load and R is the original cross-sectional area. In some other cases, for example, elastomers and plastic materials, the change in the cross-sectional area is significant. For the case of material where the volume is conserved, for example, Poisson ratio is equal to 0.5. If the true stress is desired, it must be calculated using the true cross-sectional area instead of initial cross-sectional area, as sigma 2 is equal to 1 plus epsilon E multiplied by sigma E, where the epsilon E is the nominal engineer strain and sigma E is nominal engineer stress. The relationship between two strain and engineering strain is given by epsilon 2 is equal to uh, logarithm 1 plus epsilon e to the base of e number. In uniaxial tension, true stress is then greater than nominal stress. The converse holds in comparison. Graphical representation of stress at a point. More circle Lamb's stress ellipsoid together with the stress director surface and Cauchy's stress quadratic are two-dimensional graphical representation of the state of the stress at a point. They allow for the graphical determination of the magnitude of the stress tensor at a given point for all planes passing through that point. Morse circle is the most common graphical method. Morse circles, named after Christian Otto Moore, is the locus of points that represent the set of stress on individual planes at all their orientations. So here, as you see, we have a geometry, and in this geometry, firstly, because we are using finite element method, for computing the stress and displacement and stress. We make a mesh as you see because we have an even surface here. We use equal triangulars, which is a tetrahedral type of meshing. And then we made a force. From here, you see that at the left side, I applied a 130 Newton force to the left side, while the right side is in fixture part, and also I have applied the temperature and the pressure. Temperature is about 125 Newton per square meter, and temperature is about 40 Kelvin. And finally, you can see the result of the stress, phone stress, and displacement, which is based on millimeter, and also strength. Thank you so much for watching my tutorial video until the end. Today is 28th of January 2026, and time is 6:12 o'clock in the morning that I'm recording this